Good. Now, we already talked about these rotational transitions. Classically, they would be described in terms of the rotational momentum. So the energy of a rotational transition is given by 1/2 over theta, where theta is the moment of inertia, times the total rotational momentum vector squared. Quantum mechanically, this is almost the same. It's just that we have here the quantized expression, so h squared over 2 theta, and instead of j squared we have j times j plus 1 for good quantum numbers j. Now a complication is that for in contrast to or in general, that due to the shape of the molecules, theta is a tensor because it depends on the coordinate system and the symmetries of the molecules. And so when we are transferring this into the main axis systems, theta can be described by the diagonal element of this tensor, which is theta 1, 2, 3. And we can distinguish between cases where all the three are the same. Then we have a spherical system, spherical gyro. We can find that 2 are the same. Then we have a symmetric gyro. And we can have the case that all 3 thetas are different. Then we have an asymmetric gyro. That is our molecule. So an example for this asymmetric is the already mentioned methanol, where we have here this tetrahedral configuration of the CH3, and then we have the OH term, which is here, and the other H is here. Maybe this is the O. This is even more complicated because we can have also an internal rotation here of the OH group, but let's ignore this for the moment. So looking at a symmetric gyro, we have a clear main axis, which means we can define good quantum numbers. We have 2 moments. And that is because we can distinguish between the total angular momentum and the projection of J onto the symmetry axis with theta 3. So this leaves us with the difference between J squared minus K squared, which is the angular momentum in the direction of theta 1 or theta 2. So this is the classical description here. Then we can write down the energy of this rotation. In terms of the theta 3, so k squared plus j squared minus k squared. Should be. This is a 3. And the prefactors, and so let me correct this. So this is wrong here. Theta 1 or 2, which is the same. And so we can collect the prefactors into an A for the k squared and an B for the j squared minus k squared. Or we can resort the terms here in terms not of A and B, but in J and K. So we can write BJ squared plus A minus B K squared. Quantum mechanically, we saw that the only difference in the energies was that the J is basically replaced with J times J plus 1. So we find that for the rotational energies, this can be written as B times J plus 1 plus A minus B K squared. So looking at an example, this is ammonia, NH3, which is a tetrahedral configuration. So we have here this triangular base configuration of the hydrogen atoms and the nitrogen over this triangle, with the one hydrogen here below the plane of the screen and this one here above the plane. So this is indicated here by these symbols. And for this particular case, theta 3 is larger than theta 1 and 2. As a consequence, A is smaller than B. So with A smaller than B, we have a diagram that is falling with K. So for a given J, if we increase K, the energies here go down. The K is here on the x-axis. We have the additional case that we see that every J and K state splits up into two possible cases, and that is called inversion transition, which is a particular case for ammonia and some other species. That is that there is a symmetry of this molecule, so that the N can also sit below this plane of the hydrogen atoms, which has a somewhat different energy, and the transition between the two cases, so a transition quantum, a tunneling through this plane into this configuration, is this inversion transition with a very small split of 23 gigahertz. A more simpler case is a symmetric, is a spherical gyro, where we have the case that A and B is the same, and here this term then cancels out, so that the rotational energy is only determined by the rotational quantum number J. So that means that the split between the different K values vanishes, and every J value is degenerate with a J of with 2J plus 1. So this is described by the statistical weight G, 2J plus 1. And a few important molecules, the most important is maybe CO, but here are some other linear molecules that all share the same energy level shape. We see here the example of the CO rotational levels. We have the selection rule that delta J needs to be 1. So we have here this transition from 8 to 7, 7 to 6, and so on. And you see this regular symmetry here, so that the transition frequencies always change in the same delta